directed acyclic graph, topological sort, Kahn's algorithm, shortest path algorithms like Dijkstra, Bellman, Ford, Washer, and we'll have several practice problems. So let's start first with directed acyclic graph. Now, what is directed acyclic graph? A graph that has directed edges and that contains no cycle. Now, what do we mean by directed edges? That is, if I have two nodes A and B, and there is an edge directed between A and B, so this edge is called directed. That is, I can move to edge B, node B only from node A because I have a directed edge from node A to node B. And what is acyclic? A graph that does not have a cycle is called acyclic graph. Now, let's see why do you need to know about directed acyclic graph. Let's start with topological sorting. So, what is topological sorting? Topological sorting is a sequence of nodes, is a proper sequence of nodes which we create for a graph in which if a node U comes before node B, that is, if there is a directed edge between node U and B, and U, then in the sequence, U must come before B. So the formal definition is topological sorting for directed acyclic graph is a linear ordering of vertices such that for every directed edge from U to B, U must come before B. So here basically if we write a sequence of nodes here A comma B, now we can see that in this sequence A comes before B. Why? Because the edge is from A to B. Therefore, A must come before B. So we cannot have a topological sorting sequence like B comma A. No, because B, there is a directed edge from A to B. That means A must come before B. B can't come before A. So this is a wrong sequence. The second one is wrong. The first one is correct. So this is topological sorting. Topological sorting is an ordering of vertices where if there is a directed edge from node A to node B, then node A must come before node B. Now, one important fact about topological sorting is that it can only happen in DAG, that is directed acyclic graph. Now, why directed acyclic graph? Let's see. Why not undirected graph or why not a directed cyclic graph? So here we have a graph which is cyclic. You can see that from here the edge is going to 4 and in this way it creates a cycle. Now, if I write a toposort for this graph, suppose I'm starting from 1, so I'll write 1, after that I'll write 4, after that 0, after that 5, then 2, then I have 3, and then I have 1. So basically, see, if I'm writing a topological sequence of this graph, so here 1 comes before 3, obviously, because from 1 we can move to 3, right? So there is an edge going from 1 and then it reaches 3. So therefore 1 must come before 3. But at the same time, here there is an edge from 3 to 1. So 3 must also come before 1, right? So it's not possible for two nodes where both of them must come one before the another. Like we can't have one coming before three and at the same time three coming before one. So it's not possible. So this is why topological sort is not possible for directed cyclic graph. Now why not undirected graph? So if I'm writing a topological sorting for undirected graph, I don't know where the edge points to. Like I have this edge between 5 and 2. Now I don't know that whether I should keep 5 before 2 or I should keep 2 before 5. So I don't have a proper direction. So I need a directed edge obviously since I need to know which node to keep before and which node to keep after. So it's not possible in undirected graph as well. Now we will be moving on to the next page. So these are some diagrams of topological sorting. So it can happen in only directed acyclic graph, and these are some of the graphs given and their topological sort given. You can just check them. Now, how to write the code for topo sort, or uh, what is like how to solve it, how to write a topo sort for a graph. So we have two methods, one using DFS and one using DFS. I hope you have learned about DFS and DFS in your previous classes. So what is the algorithm of writing topo sort using DFS? That is, we need to initialize a visited array to mark visited vertices, and then we have to call DFS for each of the nodes and mark the current node as visited, and then recursively call DFS. And also we need a stack. Now I will show you how to do it, but before that, let's see this portion of the code, that for each of the node, if that node is not visited, we are calling a DFS, and then we are performing certain algorithm from which we are getting the topo sort. So I'll be telling you about the infusion, but at first let's see how to solve this. So this is the DFS, how to solve it using DFS. So suppose I have this graph, okay? So I'm writing the adjacency list of this graph here. So from 0, there is no outgoing edges. From 1, there is no outgoing edges. From 2, so this is the adjacency list of the graph. Now, this is the part of the code that I just showed you. Now, for each of the nodes, let's do it one by one. Suppose I am calling from node 0 because I equals to 0. So node 0, is it visited? So no, it's not visited. So first I am calling for DFS of 0. Now it is not visited, so I am going on and marking it visited. Okay. Now I'll go through its adjacency list. Do I have any nodes that is coming after 0? So I see there is nothing in the adjacency list of 0. That means for 0, the traversal is complete. So I'll just erase this and I will just put 0 in our stack. Now I'll move on to here, come on here, and there here I becomes 1. Now I'm calling DFS for 1. Now, from 1, do I have any nodes in the adjacency? First, I'll mark it visited, obviously. So, do I have any nodes in its adjacency list? No. So, that means the DFS call for 1 is also complete. And now I'll mark it, I'll push it into the stack. Now I'll move on to 2. Now I'll call DFS for 2. Now, what is the adjacency list of 2? So there is an edge from 2 to 3. Now 2 further will call DFS of 3. Now from 3, what we have? That is, we have 1. So, so so first we'll mark 2 as visited. When we are calling 2, we'll mark it as visited. Then we are calling DFS of 3. We are marking it as visited. So let's mark 3 as visited. Now, in the adjacency list of 3, what do we have? We have 1. So I'll call further DFS of 1. Will I call DFS of 1? Now I'll see that 1 is already visited, right? So I no need to further call DFS of 1. So I'll not call it. So are there any other nodes from 3? No. After 1, there are no further nodes. That means DFS call for 3 is complete. Now I'll push it into the stack. 3. Now, from 2, after 3, are there any other nodes? No. That means from 3, we are returning, and then there is no further cause for DFS of 2 as well. So I'll now push 2 into the stack. Now I called for 2, now I becomes 3. Now 3 is already visited, so I don't need. Now I becomes 4. So I'll have DFS call for 4. Now I'll move to the adjacency list of 4. So here 4 is calling node 1, so I must call DFS of 1. Should I? No, because 1 is or 0 is already visited, so I'll not call. Now then I have another node, that is DFS of 1 from 4. But I'll not call 1 as well because 1 is also already visited. That means the DFS call for 4 is also we had already marked it visited. Now there is this DFS call for 5. Now 5 is not visited, so I'll mark 5 visited. Now from 5, I can move on either to 2, 0 or 2. 0 and 2 both are already visited, so I have no further cause for DFS of 5. So I'll finally push 5 into the stack. Now I'll pop all the elements of the stack. Now I'll pop one by one, so it will become 5, then 4, then 2, then 3, then 1, and then 0. So you can check that from 5, after 5 we can have 4, because there is no, because we can move from 5 to 4, right? There is a directed edge, so we can keep 5 before 4. There is no dependency of 5 and 4. Now can we keep so let's see for each of the edges. There is a directed edge from 5 to 0. That means 5 must come before 0. See, 5 is coming before 0 only. We have a directed edge from 4 to 0. That means 4 must come before 0. 4 is also coming before 0. We have a directed edge from 5 to 2. That means 5 must come before 2. 5 is coming before 2. We have a directed edge from 2 to 3. That is 2 must come before 3. So 2 is coming before 3. Also, you have a directed edge from 3 to 1. That means 3 must come before 1. So you have 3 before 1. And also we have a directed edge from 4 to 1. That means 4 must come before 1. So 4 is coming before 1. So this sequence is a valid sequence, right? I hope you can understand the algorithm. So for each of the, let me repeat, for each of the node, if that node is not visited, I'll call DFS of that node. If that node has any nodes, any edges with other nodes, that is, if there are any further nodes in its adjacency list, I'll recursively call DFS for all of them. Once the DFS of a node is complete, I'll put that into the stack, and I'll continue this, right? So every time I'm calling a node, marking is visited, recursively calling all the further nodes in its adjacency list, and then after the DFS call is finished, I'm putting it into the stack, and at last I'm popping all the elements from the stack, and that is giving me the topo sort of the graph. So it's quite easy, right? So that is what we are doing. This here is the code. So we are declaring a stack. We are taking a visited array and initially marking all of them as 0. We are taking a stack, and then for each of the node, if the node is not visited, I'm calling DFS of that node. Now, what I'm doing in the DFS, first I'm marking the node visited. Now, for all the nodes in its adjacency list, I am checking if that node is not visited. If it's not visited, I'm further calling DFS. And at last, when the DFS is over, I'm pushing it in the stack. And finally, I'm popping all the elements from the stack. And that is our topo sort. I hope it's clear, right? Now we have topo sort using DFS. Now, topo sort using DFS is given a term, that is Kahn's algorithm. It uses a similar approach like DFS, that is, we are going to do it using Q. So let's see how it works. First, let's read the algorithm. Okay, so let me first explain the idea behind the DFS, topo sort using DFS. So what are we basically doing is, suppose I am starting from node 5. Now, from node 5, if there is any edge, that is, I'm going to further nodes from node 5, right? So that means node 5 must come before. So I'm going to DFS call of 0, and further I'm going. And when I'm reaching the final node, I'm pushing it in the stack. And while I'm getting the answer, I'm popping in from the stack, right? So the pushing order and the actual topo sort order is actually reversed. So what you can see is, I am pushing the element first that will come in my topo sort last. That means which have no outgoing edges. Okay. So that means if a node has no outgoing edges or very less outgoing edges, that means it can always come at last, right? So at so that node will always have a last DFS call. Now, since I'm pushing it into the stack at first, when I'll pop it at last. So in the topo sort, it will already be in the proper sequence. So I am calling for 5. Now I'll at last reach such a node which has no further nodes to call. That means it's the last node. It has only incoming edges and no outgoing edges. From that node, I can go to any other node, right? So that means that particular node has no any dependency. It can come at last. The previous node has to come before that particular node, but that particular node can come at last, right? So I'm pushing that node at first into the stack because when I'm popping it, it's coming at last. So our proposal in I hope intuition is quite clear about what are we actually doing it in our DFS and how it is ensuring that we are getting the proper topo sort. Now we can move on to our DFS algorithm. So here what we are going to do is we'll calculate all the nodes with in degree 0 first. What is in degree? The number of edges that is coming towards that node. Okay. So we'll first process all the nodes with in degree 0. So we'll push all the nodes with in degree 0 into the queue. Then I'll pop them one after the another, and then I'll process each of the nodes one by one. So I'll tell you about the intuition. First, let's see the algorithm. So see, I have taken the same graph and then I have taken the adjacency list. This is my queue. Now suppose I am starting with similar thing is there for each of the node. I'll call it. Now for 0, the, here is the code. So first I'll calculate the in degree of each of the nodes. Now let me see what is the in degree of 0. How many edges are pointing towards 0? In degree of 0 is 2. What is the in degree of node 1? That is also 2. What is the in degree of node 2? 1. So in degree of node 2 is 1. Now I have in degree of node 3. That is also 1. I have in degree of node 4. That is 0. And I have in degree of node 5. That is also 0. Now I have calculated the in degree of all the nodes. Now I will first push all those nodes into the queue which have in degree 0. So what are the nodes? That is 4 and 5. Now I'll pop them one by one from the queue. First I am popping out 4. Now here I have 4. Now what I will do is I'll process this node. Now what I mean by processing, that is, see what are we doing here? When I'm calling the topo sort, for all the nodes in its adjacency list, I am reducing it to 0. I'm reducing the in degree of the nodes by 1, right? So I'll do the same here. So from 4, 4 is contributing in the in degree of 0 and in the in degree of 1. So I'll reduce the in degree of 0 and in degree of 1 by 1. So here is the in degree of 0. I'll reduce it to 1. And here is the in degree of 1. I'll reduce it to 1. Uh, so now, okay, it's so I have processed all the nodes in 4. Now I'll push 4 into my answer array. Now do I have any nodes that became 0? No. So now I'll process the next element, that is 5. Now I'll pop 5 from the queue. I'll write 5 here. Now 5 is contributing to the in degree of 2 and 0. So I'll reduce their in degree by 1, right? Because from 5, we can reach 2 and 0. So 5 is contributing to the in degree of 0 and 2. So I'll reduce their in degrees. So for 0, I'll reduce it. And for 2 also, I'll reduce it. So now I'll push C. For node 0, in degree became 0, and also for node 2, in degree became 0. So I'll push node 0 and I'll also push node 2. Now it's complete. Now I'll pop 0 from the queue. So I'll push 0 to my answer. Now 0 is contributing to the in degree of none. See? So I have nothing to do with 0, right? Now I'll pop 2 from here. So I'll pop 2. Now I have to check on whose in degree 2 is contributing. So from 2, we can reach to 3. So I'll reduce the in degree of 3 to 0. Okay, reduce it by 1. So it will become 0. Now I'll push 3 into the queue. So I push 3 into the queue. Now I'll again pop 3 from the queue. So I'll take 3 to my answer. Now 3 is contributing to the in degree of 1. So I'll reduce the in degree of 1 to 0. Now I'll push 1 to the queue. Every time our node's in degree becomes 0, we are going to push it to the queue. So I'll push it to the queue. That is, I push 1. Now I'll again pop. Now 1 is not contributing to the in degree of any node. So that means this is our topo swap. Is this valid? For from 5 to 2, 5 must come before 2. So 5 is coming before 2. From 2 to 3, 2 must come before 3. 2 is coming before 3. 3 must come before 1. 3 is coming before 1. 4 must come before 1. 4 is coming before 1. 5 must come before 0. That is also valid. And 4 must come before 0. So for all the edges, it's valid. So what are we basically doing is, for each of the nodes, we are calculating the in degree. Every time the in degree is becoming 0, we are pushing it in the queue. And how are you processing each of the nodes? We are popping them from the queue and we are checking for which of the nodes it is contributing in the in degree. Now, how will I get for which of the nodes? Basically, I'll get it from the adjacency list. Like for 5, it is contributing to the in degree of 0 and 2. So for 5, I can directly check to the adjacency list. It has 0 and 2. So that means it is contributing to the in degree of 0 and 2. Now, what is the ideology behind that? Similar thing that I said for the DFS, that if I have in degree 0, that means I am not dependent on any other node. I don't have to come before any other node. I have no out degree, right? I have no edge going out from me. So that means I have no dependency. So I can basically come at last. That is the ideology behind it. So similar, we have the similar ideology. If I am having in degree 0, that means I have only outgoing edges. So I can come first, right? If I have out degree 0, that means from other nodes, edges are coming to me. So other nodes have dependency. I have no dependency. So I can come at last. This is the ideology of DFS. But for DFS, we are doing the opposite. We are starting from the node where in degree is 0. I have out degree, but I don't have any in degree. So I can come at first. I can come before in node. So I'll just push that particular node which can come at first in the queue and then pop them. So I'm getting the nodes in the similar fashion. I'm pushing it into the queue. That's why you are using a queue, right? So this is the topological sort using Khan's algorithm. I hope it's clear. So for DFS, we are using stack and we are thinking the intuition is any node that will come last in the topo sort will have an out degree 0. So that is the similar approach. So that particular node I am pushing into the stack first because that will come pop out at last. And for Khan's algorithm, my ideology is that any node that has in degree of 0 will come first. So I'm pushing it to the 2 first, and then it's coming out first. So it is coming first in our answer. This is the similar thing. So you can see that the topo sort that we got from DFS and the topo sort that we got from DFS are different, but both are valid. So it can happen that topo sorts for two different persons can come different, but both can be valid. Now, one important thing is, what if we do it for directed cyclic graph? So for DFS using TopoShot, if you do it for any directed cyclic graph, it will not be able to detect it. It will give a particular sequence, but then if you start from any other node or do some other changes, you can just get another sequence. So it's not actually valid, but you can't prove it using DFS. So for proving that for a graph, a topo sort can't be formed, we use Kahn's algorithm. So what happens? Either we get no node with integer 0 at first, or in our answer will not get all the nodes. So all the nodes will not appear in our answer. So this is the thing. If you want to know, if you apply toposort in any graph that is cyclic, so you will not get all the valid nodes or a valid sequence using Kahn's algorithm. So I hope it's clear. Now we'll move on to a question. What is the question? We have the question that is course schedule. But it says there are a total of n courses you have to take from 0 to n minus 1. You are given an array prerequisites where prerequisite I is AI, comma BI indicates that you must take course BI first if you want to take course AI. So that means for taking AI, I need to take BI first. That means I have a directed edge from BI to AI, right? Now, for example, for the pair 0 and 1 indicates that to take code 0, you must take code 1 first. So that means if I apply topo sort in this, that means I need 1 to come first before 0. That means I need to have a directed edge from 1 to 0. Now return the ordering of courses you should take to finish all courses. If there are many valid answers, return any one of them. If it's impossible to finish all courses, return an empty array. So to check if it's impossible, we can directly apply Kahn's algorithm, and if you are not getting all the nodes, that means it's not possible. So we'll basically return an empty array. So this is the code for using DFS, that is Kahn's algorithm. But you can do it using DFS. I want you to do it using DFS. By using DFS, you might not be able to get if it's not valid, but at least you will learn how to apply it. So basically what we will do is, I'll show you using DFS. You can check the code using DFS. So for each of the node, I'll keep a visited array. This is my adjacency list for the given example. So for node 0, it's not visited. So I'll go and mark it as visited. Now from node 0, so first basically I call DFS of 0. Now from node 0, I can call 1. So I'll further call DFS of 1. Now it's not visited, so I'll mark it as visited. Now from 1, I can call, from 1, I can call DFS of 3. Again, it's not visited, so I'll mark it as visited. From 3, I don't have any further nodes to go. So that means DFS call for 3 is done. I'll push it into the stack. Now 3 is done. Now I'll come back to 1. Do I have any other nodes to call? No. That means DFS call for 1 is also done. I'll push it into the stack. I'll come back to DFS of 0. From DFS of 0, I can also call DFS of 2. So from here, I'll call from DFS of 0, I can also call DFS of 2. So I'll call DFS of 2, right? Now from DFS of 2, I can also call DFS of 3, but 3 is already visited, so I will not call. Can I call any other node? No. That means DFS call for 2 is completed. So I'll push it into the stack. DFS call for 2 is completed. Now from 0, can I call any other node? No. That means DFS call for 0 is also completed. So that means 0 is also completed. Now I'll come here for I equals to 0. For I for I equals to 0, the DFS call is complete. Now for I equals to 1, it's already visited. For I equals to 2, I forgot to mark it visited. Okay. So we have already processed 2, so it is also already visited. Now for I equals to 2, it is also visited. For I equals to 3 is also visited. Now for I equals to 4, see, we have not, it's not already visited. So I'll call DFS of 4. So there is no further nodes. It had, suppose it had 4 and all, then we would call, but there is no further nodes. So we can just call till V. So here V is only up to 3. So there are no further DFS call. So this is, now I'll pop it from the stack one by one. So first I'll take 0 out, then I'll take 2 out, then I'll take 1 out, and then I'll take 3 out. Now you can check if it's a valid sequence or not. It will be valid. So you can apply this using DFS or DFS, but since this has a condition that if it's impossible to finish all the courses, then return an empty array. To check this, you need to apply DFS, because if you apply DFS, the resultant array will not contain all the nodes. So you can just check the size of the array. If it doesn't contain all the nodes, that means it is not a valid graph for TopoSort. So you will just return an empty array. So here is the code. I'll just go through the code once. So what happens is, so I am calculating in degree for each of the nodes. Now while Q is not empty, I am taking out Q front, and then I'm popping it out from the queue, and then I'm pushing it to my answer. Now for all the adjacent nodes of that node, I'm reducing their in degrees, and then I'm pushing it into the queue again if the in degree is 0. So I'm checking if the in degree becomes 0. If it becomes 0, I'm pushing into the queue. Now at last, I am checking the condition. If our resultant array size is equal to n, that means it contains all the nodes. It states that our topo sort is valid. So I'll return the answer. And if it is not valid, so I'll return an empty array. So I hope it's clear. Uh, any doubt? Okay, so if no further doubts, the following section will be taken by Aman.
I'm audible and my screen is visible. Just give a thumbs up if I'm audible. You just give me a thumbs up if I'm audible and my screen is clearly visible so that we can start from our next topic. Okay, so let's start from our next topic. So till now, we have discussed in graph section, we have discussed DFS, PFS, and then we have discussed TopoShot. And in TopoShot, we have discussed like TopoShot using BFS and TopoShot using DFS. So now let's start the new topic, which is the next topic of graph, and that is the shortest path algorithms. So there exist different algorithms for finding shortest path in graphs. We are going to study 3 different algorithms here, and that will be Dijkstra's algorithm, Bellman-Ford algorithm, and Floyd-Warshall algorithm. Right. So before jumping on to the algorithms, let's see what is shortest path. Okay, so let me just copy this and let me show you in what is shortest path. So till now, you have seen the graphs whose edge weight was 1 in every case. So those graphs were called the graphs with edge weight 1, and this is the graphs with some edge weight. Like till now in trace as well as in the today's earlier section of the class, we studied graphs without any edge weight, but now we will be dealing with the graphs which contains some edge weight. Okay, so let me tell you what is shortest path. So shortest path between two nodes is the path along which the sum of edge weights along that path is minimum. Like if I want to find shortest path from here A to C, okay, so with there exist lot of paths like A to B. This is one path, and this is one path, this is another path. So there exist lot of paths between the given two nodes, but we want the shortest path. So for here between A to C, I think, yeah, this one is the shortest path, which is taking 1 plus 1 plus 5 is equal to 7 cost for reaching from A to C. So this is the shortest path between A to C, and there exist lot of paths, but we are trying to find the shortest path. So this is about shortest path, and you can see here also, like there are several nodes and there are a lot. This is my starting node and this is my ending node, and there are several paths between A to F, and we can go via this path, we can go via this path, but one of them is shortest path, and for here this is shortest path. We can go from A to C, then C to B, and then E to D, and then D to E, and then E to F. So this is the shortest path for reaching from node A to F. So this is about shortest path. So there are a lot of algorithms to find shortest path in graph. So we will be starting with the very first algorithm, that is Dijkstra's algorithm. And in most of the CP questions, whenever we see any shortest path question, then we use this algorithm. So let's see what this algorithm says. So before jumping onto the algorithms, let me tell you what we are trying to find here from the algorithms. So we are trying to find, like we will be given the graph. Okay, let me take the same graph. And we are trying to find, we will be given a source node. Let's suppose this is our source node for now. And we are trying to find the minimum distance from source node to every other node. Okay, so we want to find the minimum distance from the source node to D, to B, to E, and to C. So we will be given a source node, that is S, and we need to return the minimum distance from the source node for a path starting from the source node to all the other nodes. Like you can see here, the starting node is A, and so the minimum distance from the starting node to starting node itself is 0, obviously. And from A to B, like it is given that from A to B, the minimum distance is given 3. It means this is the minimum distance. We can go via this path as well, but this is giving a distance of 6, but this is giving a cost of 3, right? So this is the minimum cost between A to B. Okay, so let's see how Dijkstra's algorithm works, and let's try to implement Dijkstra's algorithms and see what is the intuition behind Dijkstra's algorithm. So in Dijkstra's algorithm, we follow some steps. So firstly, we make an array, that is distance array, and whose size is equal to number of nodes present in the graph. So here there are 5 nodes. So I'm making a distance array of size 5. Okay, so let me denote this as A, and this as B, C, D, and E. Okay, so generally the indexes are from 1 to 5, but let's assume for now that these are from A to E, and we use a data structure that is priority queue, and this is a min-nib priority queue, which stores the minimum element present in it at top. So we can access the minimum element present on top in logarithmic time complexity, and we will see why we are using the minimum. We in case of Dijkstra's algorithms. Okay, so let's start the algorithm. So we start the algorithm with, we know that we're trying to find the shortest path starting from the source node to every other node. So the shortest path from source node to source node itself will be always 0, right? So initially fill all the nodes with a distance of int max, because int max is denoting that we are we are not able to reach those nodes. So I am leaving this blank for now. It means it is denoting that int max is stored here. Okay. So initially from source node to source node the distance is 0. So we will put here 0. It is denoting that here the C is denoting that the minimum distance required move to move from A to C via any of the path. Okay. So our base case is this. So just push it into Q, and Q will store two things. That is distance. It will store a pair of distance comma node. Okay. And initially we are reaching to node A in distance 0. So we will push it into the queue, priority queue. Okay. And we will start the algorithm. So the algorithm goes like this. We start with the top element of priority queue. Obviously, the top element will be minimum element, and here only one element is there. So this will be our top element. So we pop it out, and so after that, as we know that we are at the current node A, and we are reaching at node in distance 0 as we have stored here. So after this, we visit all its nodes which are adjacent to it. Like here, the adjacent nodes are B and adjacent nodes are C, right? The edge width of this edge is 1 and this edge is 6. So now we visit all the adjacent nodes and check that we know that we are reaching this node by by putting a cost of 0. So we can reach this node by traversing through this edge, and 0 plus 6 will be 0. So we can reach this edge by investing a cost of 6. Okay. So after this we will check that it 6 is lesser than the term stored in the distance of B. So here it is stored int of max, and obviously 6 is less than this. So we will update this as we are reaching to B by a shorter part than it was stored previously. Okay, so we will update in this, and at the same time we will make sure that insert here with the distance and node. So we will insert it here with the 6 and the node B. Okay. So we have traversed one adjacent node. Now for second adjacent node, we are reaching here to 0. So we can reach here with 1 by this path. So we can reach here by in 1, and we will check that 1 is less than the value stored in distance of C. So we will update it and we will push it into our priority queue. Okay. So we are pushing it. So we can reach this to C in one distance and the node is C. Okay. So I'm not putting the elements in priority queue in order. We will always extract the minimum element. Okay. So after this we have traversed all the adjacent nodes of it. So okay, so we will just pop it out, and I've already cut it down. And then we again take the next element which is at top. Now why we are taking every time minimum element? Because we want to find the minimum distance to every node. And when we consider minimum element, so we are considering the distances which are minimum first, so that by those paths we can reach to the another nodes, and those distance will be minimum. Okay, so next we will pop this out, and our current node is C, and we are reaching here to in distance 1. So we will check. So it is not C, like it's my mistake, like it was D. So and we are reaching here to 1. I misinterpreted this as C. So let me write it is just D. Okay, so now we are at the current node D, and we are reaching it here at distance of 1. Now traverse its all the adjacent nodes. Here its adjacent nodes are A with edge width 1 and it's E. with edge weight 1, right? So after this, traverse all the adjacent nodes present for D. Here we are reaching at C, so here we can reach at with a distance of 2, and here we can reach also at with a distance of 2. Now we will check, are we reaching adjacent node at a less distance? So obviously it is not less than 0. So as we have already reached via shorter path before, so we will not update it and we will not push it into our priority queue. So don't push it. Now let's check for E. So are we reaching here? We are reaching here at a distance of 2, right? So are we reaching here at a less distance? So yes, the int max here is stored. So we will update it and we will push it into our priority queue. Okay, so just push it here 2 comma E. And so we are done with the current node. So let me just erase this. Okay, now push the top element of priority queue, and obviously between these two, top will be this, as this is minimum. So I'm popping this out, and now my current node is E, and I'm reaching here at a distance of 2, right? So we will visit all its adjacent nodes. Obviously, we will not reach D. We will not go to D because for going D, it needs a cost of 3, and already in D, a cost 1 is stored. So we will not visit D. And for B, we are reaching here at 2, and by this path, we were reaching B. Let me just show you. We are reaching B by adding a cost of 2. So 2 plus 2 is giving me 4. So we are reaching to B 4, and we have seen that the 4 is less than 6. So let me just update it as we get a shorter path. So it will be updated with 4, and we need to push it into our priority queue, right? So just push it into our priority queue with 4 and B. So we have seen this, and let's say for C, its edge weight is 5. So we can reach to C via this path, and which will take 2 plus 7, as we have already calculated for it. That is 2 plus 5, that is 7. So we are already reaching C here. Int max is stored. Okay, so we are reaching here at 7. So we will just update it and we will push it into the queue, priority queue. Okay, so let me just erase the elements which are not present here, so that it will be better to visualize. Okay, so next we were reaching to C in 7 cost, right? So we will update 7 comma C. Now the top element will be this, right? So here top element will be this. So just remove this, and from B, just check it's all the adjacent nodes. In A, and here we are reaching with distance of 4. So we can reach A to 4 plus 6, 10, which is not less. So ignore it. And for E, we are reaching to 4 plus 6. So already 2 is stored. So just ignore it. And for C as well, 4 plus 5, 9. So we will insert no nodes because we have already stored already a shorter path than this. Okay, so now the next step is to pop this, as this is our top element, right? So 6 and B. So now as we can see, this distance is already bigger than this. So there is not any meaning of proceeding further and checking all its adjacent nodes, because we have already, when we were storing this 4, then we could have already seen that by visiting all the adjacent nodes via shorter path. So just ignore this. And so this is the last element, and we will pop it out and see with C we are reaching to 7, right? So here going to any adjacent node doesn't make sense here as well, because we will not get any shorter path. So this is how we see things happens in Dijkstra's algorithms, and we keep we keep pop out from for the node from which are at the top of the priority queue, because it gives it we can access the nodes minimum node which are present in the priority queue in just logarithmic time complexity. So it is time efficient as well. And we check all its adjacent nodes that can we go to the adjacent nodes via current node. So if the distance is minimum, so we will update it and we push it into the priority queue, and we keep doing like this. And hence we always get the, at the last, we always get the stored in the array, in the distance array, we always get that the minimum sum required to reach the every node from the my starting node. Okay. So this is how we proceed with Dijkstra's algorithm. So okay, so let me, so here it is written the same thing what I did in my driver. Initially insert the source vertex into the priority queue, and until the priority queue becomes empty, keep doing the same task, extract the vertex with the minimum distance, okay, and relax all its adjacent edges. Relaxing here means try to visit all its adjacent nodes, and if you find that you are reaching to adjacent nodes with a minimum cost, then that is stored in that node. Okay, so update this node, and here the term relax is used for that. And if the shorter distance is found, update it and push adjacent vertex into the priority queue and proceed this. And at last, you will get in the distance array the minimum distance required to reach that node, starting from the starting node. Okay, so here you can see in this example. Okay, so as I have explained the Dijkstra's algorithm, so let's see how we can implement this. Okay, so its implementation is very simple. Like here, I have just taken input of my adjacency list, and a source node will always be given because Dijkstra's algorithm is a single source algorithm. So a source node will be given, and so we are calling the Dijkstra's algorithm here. And initialize a priority queue of min heap. Like you can see here in the syntax, we have initialized a min heap priority queue, and initially the distance, the minimum distance required to reach the source node is 0 because we are starting from this node only. So just push this 0, this is distance, and this is the node number. Okay, and until our queue becomes empty, process current node and pop it out. And if d is not equal to distance of node, it means we have already reached to current node via a smaller distance. So we have already processed the smaller distances from my current node. So just continue from here, and thereafter we will visit all the adjacent nodes. And if we can relax the adjacent nodes, I mean, this is the d is the distance required to reach the current node, and if by traversing through the current edge we are getting the less cost, then we can update it and just push it into the priority queue. Okay, always make sure to push this into the priority queue, otherwise you will miss some shorter distances. Okay, so let's okay, so after, here is a flow as well that we can't detect in Dijkstra's. Like what if the edges contain a negative weight? So let's see what happens in this. So suppose if we have edges with 1, 2 and a -1. So can we find the shortest distance to reach node 2 starting from this? No, because initially, like we have stored in its distance array, suppose we have stored 0 and 1. Then what will happen here is, if there is any negative weight, edge width, then we will always find the shorter distance and we will keep traversing from the array here. And sorry guys. Okay, so okay, so we were discussing like it doesn't work for a negative weight because here I have 1 and here I have 2. So if a negative edge width will be there, so we will always keep updating the node distance from 1 to 2. And if we reach 2, then we will always keep updating the distance from 2 to 1 because we are always reducing the distance to reach here. So it will always keep reducing the distance, and several nodes will be pushed into the priority queue. And our priority queue will never become empty. So that's why we can't use the extra algo for a graph edge width. So we will see that there are some other algorithms which we use for this. Okay, so let's see the next algorithm, which is the next algorithm is Bellman-Ford algorithm. Okay, so we will see how it works for negative edge widths as well, and it works for the detection of negative cycles as well. Okay, so before this, let the time complexity for the Dijkstra's algorithm is E into log of B, because log of B is the time taking for the doing pop operation from our priority queue, and here you can see we are taking the space complexity of big O of V, where V is the number of vertices, and this space complexity is for the distance array. Okay, and we are taking some space complexity for our priority queue as well, but we are just ignoring this. Okay, so let's start discussing the Bellman-Ford algorithm now. So let me take this example for showing how Bellman-Ford algorithm works. Okay, so let's see. So here you can see there are a lot of negative edges. So obviously Dijkstra's algorithm would not work here. So we need to use some Bellman-Ford algorithm. So what we do is in Bellman-Ford algorithm is like we need some edges. Okay, so let me take this. So in Bellman-Ford algorithm, these are the edges. These are nothing but just edges. Like you can see, this is edge. This is of the form U2V. Generally, this list is given as an input, and this is of the form U2V, and here is weight. It means there is an edge between from U2V and with edge weight W3. Like here, you can see the edge weight is from 1 to 2. Okay, so the first edge is denoting from 1 to 2, and it is 6 edge width. So here it is given all the 7 edges, 3 and 4, 7 edges from 1 to 2, that is 6, and from 1 to 3, the second edge is 5, and 3 to 2, 3 to 2 here it is. So all the edges are given just here, nothing else. So the concept we use in Bellman-Ford algorithm is we keep relaxing the edges n minus 1 times, okay, where n is the number of vertices, and here the number of vertices is 5. Okay, so what we do here is we keep relaxing the all the edges n minus 1 times. Now what I mean by relaxation here is, okay, so let me just write these edges here so that it would be better to visualize and do a dry run for showing how Bellman-Ford algorithm works. Okay, so instead of writing here, let me just write it on this side. Okay, so this is our edges. Okay, so we do here the relaxation of all the edges n minus 1 times. N is the number of vertices. Now, why n minus 1 times? I will tell you about this later. So, what is relaxation here means? Here also, so Bellman-Ford algo is also a single source algorithm, and here also we try to find the distance of every node from a source node. So, suppose I'm supposing that this is my source node, that is 1. So, here also we need to make a distance array. Okay, so let me make a distance array with 5 nodes, and initially int max will be stored in it as we did in Dijkstra's algo. And initially, as we know that for reaching 1 to 1, it means source node to source node, it will take a zero distance. Okay, so just fill 0 here, and for rest of the other places int max is filled. I'm assuming that the empty space is representing int max. So this is 1, 2, 3, 4, 5. So now let's come back to what is relaxation. So we will keep iterating from the vertex as it is given in the input. We can keep iterating the vertex in any order. So let's start from as it is given in input. So what we do, we come here at the first vertex and we see that. So from D, this is suppose my distance array D. So distance of 1, we see here that if we reach distance of 1 plus the edge width 2, if it is less than distance of 2, right? There is an edge from 1 to 2 and that is of edge width 6, right? Okay, so there is an edge from 1 to 2 and that is with distance of 6. Okay, so if it is less than this, so then we will update the distance to reach 2 and we can see that this is initially 0 and 0 plus 6 will be less than this distance of 2, which is infinity. So we can reach here at 0 plus 6, that is in distance 6. Okay, so this is relaxation. I mean, if from the current node we can reach to its adjacent nodes in less cost. So we will keep updating it like this and we iterate from first to last and we keep updating it like this. So for second node, what we do is distance of 1. So I'm just writing 1. This is my node distance. Okay, so let me write it. So for second edge, distance of 1 plus a vertex 5 is less than distance of 3. Distance of 3, yeah. So distance of 1 is 0 and plus 5 is less than distance of 3, which is int max. So yes, it is less. So we will update it. Okay. So we will update it and after this, so let me just erase this. In similar manner, we will also proceed for these steps like from 3 to 2, distance of 3, which is 5 and 5 minus 2. So we can reach to 2 in minus 3. So we get a shorter distance. I mean, previously we were reaching from 0 to 2 via this step. So it was taking a cost of 6. Now we are reaching 0 to 2 via this path. Okay, so it is taking a cost of 5 minus 2. So this is 3. Okay, so we will just update it because we get a shorter path. Okay, so just update it with 3. Now we have processed till here. So now we will see the next is distance of 2 plus minus 1 is less than distance of 4. So distance of 2 is what? 3 minus 1. Is it less than distance of 4? So what is distance of 4? It is into max now. So yeah, it is less. So 3 minus 1 is 2. So we will store here 2. Right. Now we will move to the next stage, that is distance of 3 to 3 plus 4. Distance of 3 is 5. Okay, plus 4. It means 9 is less than distance of 4. So no, so it is not less. So we will not update anything because the distance of 3 here is stored 5, right? And the edge width here in the fifth edge is 4. So is it less than distance of 4? No, it is not less, as distance of 4 is 2. So we will not go through this path as we are already going from this path and this path is optimal. So we will not update it because it is not less than this. So just move to the next edge and distance of 3 plus distance of 3, that is 5 plus 3. Is it less than distance of 5? So yeah, it is less than distance of 5. So just update it here. And distance of 4, that is 2 plus 3. It means 5 is less than distance of 5. So yes, it is less. So we get a shorter path here, right? For 5, we are reaching from now. We are following this path. 5 minus 2 minus 1, that is 3, and 3 plus 3. So yeah, 5 plus, so here it should be 6. So now, so we call this as one relaxation. We have relaxed all the edges for one time. So similarly, if we keep going like this and relax all the edges for n minus 1 times, then at the end, our distance array will store the minimum distance required to reach all the nodes starting from the source node. Okay, so we can keep doing like the same operation. Okay, so after this, let me tell you why only n minus time, n minus 1 times. Why not more times, and why only n minus 1 times? So suppose if we have a graph like this, suppose if I have a straight graph like this, 1, 2, 3, 4 with edge weights 3, 2, and anything like minus 5. Suppose if edges is given like 1 to 2, 1 to 2 is okay. So suppose if edges is given like 1 to 2, first edge is given as 1 to 2 comma 3. Okay, and second edge is given here. Third edge is given here 3 to 4 with minus 5. Suppose if our input is given like this, so we have to process from top to bottom, right? So if we come at here, we as distance of initially only distance of 1 will be filled, that will be with 0. So we will come at here distance of int max plus this. So we will not update anything here, right? Okay, let me just denote here is 5. Okay, so we'll come here and we will not update here because distance of 3 is int max. So we will just go to the next node. We come here, we don't update it here. Now thereafter we come at 1 and we say that distance of 1 is 0 and plus 2, that is plus 3. So we can reach distance of 2 at a cost of 3. So yeah, here we can reach 3. So you can see in one iteration only one node is updated, that is distance of 2. So int max is filled in 2 nodes as it is. So in next iteration, as we have computed the value for 1 and value for 2, so in next iteration this work will be done for this test case. So we will move to the full and we will compute our distance of 3 in our second iteration, and in third iteration this work will be done, right? As we have computed the distance of 3, so we will have the distance of 4. So you can see if we will be given edges in this order in which the source node will be at the bottom, so we will update only one node in our first iteration. So we have to keep iteration up to n minus 1 times. Okay, now the question is why only n minus 1 times? So n minus 1 times we need to do iteration because in a graph which consists of n nodes, suppose in a graph we have n nodes. So for any path we will visit at least n minus 1 nodes, right? Excluding this, suppose if I am starting path from here and trying to find any shortest path from for any other node, so do you think that we will visit any node twice? No. Okay, even if this is a negative weight, so for now I am saying that okay, so let me say that it is a directed graph. So we can visit at most n minus 1 times in a simple path. Simple path means no node will be repeated. So this will always give a minimum distance, and moving a node is same moving a node same twice, so it will not give a valid path, and the distance will always increase by moving a node more than once. Okay, so as we can reach as we can visit only n minus 1 nodes at most from for finding a path between two nodes. So that's why we use the iteration exactly n minus 1 times. We relax the edges. And so what if here a concept comes of negative cycle? Suppose if we have negative cycle, okay, let me say this as a okay, let me just erase this. So suppose if I have a negative cycle. So what is a negative cycle? I hope you know this. So this edge is directed from 2 to 1. So this is a negative cycle. It goes like a cycle in directed graph, and this is a cycle. And if suppose your edge weights are 2, 5, and here suppose it is minus 10. So the sum of edge weights in a cycle is here 2 plus 5 minus 10, that is minus 3. So if it is negative, then we say it as negative cycle. So what happens in Dijkstra's, Wellman-Ford algorithm is after relaxing all the edges for n minus 1 times, we get some value, right? We get some value to reach these nodes in minimum cost, right? So if there is exists a negative cycle in the graph, then we, in the nth iteration also, in nth relaxation also, we can get a lower value than this because we will keep moving this cycle again and again. Okay, we will keep moving this cycle again and again, and it will give us more shorter cost than the, the cost stored in the first n minus 1 relaxations. If there will not be any negative cycle, so these things will already store the minimum cost as we can visit at least at most n minus 1 nodes only. But if it contains a negative cycle, so we can relax it further. So to check whether a negative cycle exists in a graph or not, we can use this algorithm, and after n minus 1 relaxations, we can check nth relaxation if any node is updated further. If any node's distance value is less than the distance value for first n minus 1 relaxation, it means there exists some negative cycle which is again reducing the cost for reaching that node. So these are the things which we can use from Bellman-Ford algorithm. So here let's go through the nodes once. So it is written the same algorithm which I have discussed. Like initially, the distance of source vertex as 0 and all vertices as infinity, and relax all the edges exactly v minus 1 times. Okay, and then perform one more iteration over the edges. If any distance can still be updated, the graph contains a negative weight cycle. So we can get and we can find the negative weight cycle from this algorithm by checking if the value in the nth iteration, nth relaxation decreases. So it means a negative cycle must exist in the Bellman-Ford algorithm. So I hope it is clear. So let's move on to the code part of it. Okay, so this one is the code, and so this is just the I'm taking input. Okay, and this is the function for Bellman-Ford. So we are not doing anything extra, like we are just relaxing edges v minus 1 time. Okay, this is our distance array, and initially distance of source is 0, and v minus 1 times we are starting the loop from 1 and going till v. Okay, and for every edge, this is our u, this is our v, and this is our edge weight between u to v. So if it is not in int of max, if it is int of max, then simply skip it because we will not get any shorter cost. But if it is int of if it is not int of max, then we will check. So the distance required to reach u plus weight, and if it is less than distance of v, then simply update it. Relax it. So we will get a shorter cost to reach v via u. Okay, so and if we want to check for negative cycles, so perform one more iteration, and if we get a h width less than the h width stored in the distance array for every node, so it means a negative cycle exists and which is relaxing the nodes again and again. Okay, so this was all about Bellman-Ford algorithm, and I hope it is clear to everyone. Okay, so now let's move on to our last algorithm, that is the fluid Warshall algorithm. Okay, so till now we have discussed the express algorithm and Bellman-Ford algorithm, and which works on a single source, which is a single source shortest path algorithm. What I mean by single source is like in those algorithms, a source was given to you, and we need to find the shortest distance from that source to every other node. But what if we need to find the shortest distance between any pair of the given nodes? So in that case, we use fluid Warshall algorithm, and it is a multi-source algorithm, and we will see that we use some concept of PP here. Okay, so this is example of fluid Warshall algorithm, and so let's see what we do in fluid Warshall algorithm. So this is like bit complex example. Let me show you fluid Warshall algorithm on this example only. Okay, so as I told that it is a multi-source algorithm, and we are not fixing any source here like we were doing in the express algorithm and Bellman-Ford algorithm. So here what we do, we made a adjacency matrix. Like in previous questions, we were doing adjacency list, but here we use the adjacency matrix. And here, as we have 5 nodes, so let me just denote it as all the row numbers. Okay, so here the okay, so here the in this is distance array in which we will store the distance between every pair of nodes, right? So to suppose here 2 comma 4 is denoting that the where we will store here the minimum distance required, to reach from node 2 to node 4 via any of the path. Okay. Suppose here we will store the minimum distance required to reach from node 5 to node 3. Okay, so our distance array is denoting this. So let's discuss how this algorithm works. So initially, as we know that from node to node itself, we can reach in a zero cost. So the store in every node to node itself, I mean in diagonal, the store 0 because we can reach from node to node itself in zero cost, right? So and after this, also store the edge width of all the edges. Like here, all the direct edges. Like here, it is given 1 to 2, so 6. So store it 1 to 3, that is 5. Then 3 to 2 minus 2. So 3 to 2 here it is minus 2. And then 3 to 4 it is 4. Okay. Then 3 to 5 it is 3. So just store all the edges. Okay, and 4 to 5 is okay, 4 to 5 is 3. And 2 to 4 is minus 1. So we have stored all the edges edge width here so that we can proceed with our algorithm further. So what we do here is we try to visit from a node via every node. Suppose if I want to find the distance between node 1 to node 4, so we try to go via every node. Okay, so either we can go via 2, whether it is a direct edge or not, but we can go via following a path if the path exists. So we will try to go via every node. So firstly we try for 2, we can try similarly for 3, that can we go via from node 1 to 4 via 3, and similarly for all the other nodes. So for the given pair of nodes, we try every possible nodes that can we go via this node. So that's how here algorithm works. Like suppose here if I want to check that can every nodes go via, we consider every pair of nodes and check that if I'm visiting the nodes this and trying to go via one. So for this, okay, let me just do a try run for this. So if I want to go via one, so what I do is I will check here. So distance of like 1 to, we want to go from 1 to 1 via 1, right? So it doesn't make any sense for going from 1 to 1 via 1. So let's see for 2. So if we want to go from 1 to 2 via 1, so it will be distance of 1 and distance of 1 to 1 and distance of 1 to 2. So we will compute this, and it is distance of 1 to 1 is 0 and this is 2. So it will be 6, and already 6 is stored in this, so don't update this. Then next we will check 1 to 3 via 1. So 1 to 1 we are reaching 0, and 1 to 3 we are reaching at 5. So don't do this. Now we will check for 4, that from 1 to 1 we are from 1 to 1 and then 1 to 4. So 1 to 1 we are reaching at 0, and 1 to 4 we are as it is int max. So already int max is stored here. So like initially, suppose that every empty place had stored int max. Okay, so that's how we keep checking for every node. Like if we are here, so if we are here at 4, I want to check for 4 to 2 via 1. So we will see that if can we reach 4 to 2 via 1, it means distance of 4 to 2 plus distance of 4 to 1 and distance of 1 to 2. It means we are trying to reach 4 to 2 via 1. So if it is computed, then it will give something. And similarly, we can try for every node. So if we try for these nodes, that for every pair of nodes, we are trying to reach via 1. So this will be one iteration. So similarly, we can try for every possible node, that every pair of node, and choose a intermediate node from 1 to n. From 1 to n, we will try for every node as intermediate node, and we will check for 1, we will check the entire matrix. For 2, we will check the entire matrix, and so on for n. And we will keep updating by this method, that is distance of I, the distance of my current node, and this, suppose this is node of via, plus distance of via and the distance of j. If this is less than the distance stored in I comma j, so update the distance stored in I comma j via this sum, that we are now reaching via a shorter cost. So you can see that we are considering every possibility here. Okay, we are exploring every possibility here, that if we want to go for from a node to any other node, so we are considering every nodes as intermediate node. Okay, so all the diagonals will definitely be 0. And so yeah, we can, so if here we are using the concept similar like dp, because we are computing this thing and we are using the same thing when we are going forward. Okay, so if this thing will be computed, so we can use it for finding the distance for this node. So this is like dp. In dp, we generally recompute things and use it further for any better solution. So here we are also checking for better distance from this node. If this, suppose this thing will be computed first and this thing will be computed first. So now we are trying to compute this with the help of these two things. So it seems like DP here, and we are using the pre-computed values in the distance array. And so you can, let's say, okay, so this is the, okay, so this one is the third version, and this is the algorithm we are following here. We are initializing the distance matrix from the given graph and setting from every vertex to itself as 0. And we are considering every node as intermediate node 1 by 1. And if distance of I to j, we are storing from distance of I to j, that is minimum of distance of I to j, which is the previous value stored in it. And if this value distance, I mean distance of I to k, k is like a via node. So if distance of I to k plus distance of k to j is less than this, so this value will be stored in distance of I to j. Okay, so we are considering every possible path here. So, but what if a negative edge weight exists in the path? So can we detect a negative edge weight from the fluid Varsal algorithm? Okay, so let's see, can we detect a negative edge weight or not? So now, as from 1 to 1, 0 edge weight is stored. So if a negative edge is exist in the graph, then this thing it will become negative. Okay, because if, suppose, let me give you an example, like if this is a negative edge weight here from 2, and if a negative cycle exists here, this is suppose 5 and this is like -6. So initially we stored that we are reaching here at 0, but if a negative cycle exists here, then we will reach from 1 to 1 via this path, and -1 plus 5, and suppose this is -7 plus 5 -2. So -2 will be stored in it, right? So if for 0, if just check for the every diagonal elements, and if for reaching for from the current node to current node itself is becomes negative. It means a negative cycle exists in the graph, and we can check this also through Floyd-Warshall algorithm. So, what is time complexity of this? It's time complexity of the code is big O of V cube and space complexity of big O V square. That V is the number of vertices, and the space complexity is for the distance array, and time complexity as we are iterating for 3 loops. So let's go through its code once. Its code is like very simple. We are just iterating running a 3 loop. This is the outer loop is for via that we are iterating from node I to j via k. So we are trying every possibility of I to j, and this is my intermediate node. So if we are just storing distance of I to j is equal to minimum of distance of I to j and distance of I to via, I mean kth node, and plus distance of k to j. So we are just keep updating it via and trying every possibilities here. So this was all about Floyd-Warshall algorithm. So at last, as we have studied all the 3 algorithms, so let's just compare all the 3 algorithms. So here you can see that in Dijkstra's algorithm, we were finding the shortest path starting from the source node and using priority queue, and it has been some points are mentioned here. And in Wellman-Ford algorithm, we were detecting the negative edge width and negative cycles as well, and it was taking the time complexity of e into log v, something like that, and this was taking a string of square time complexity, and this was taking a cube time complexity. So in CP, generally we use mostly the Dijkstra's algorithm in because it is a efficient algorithm. So whenever you see a question of related to shortest path, so always try to think about Dijkstra's algorithms. So this was all about today's class, and in today's class, let me go through the ones what we have discussed. In today's class, we have discussed the topics like topological sorting and cancel algorithm, and we have discussed that things like Dijkstra's, Bellman-Ford, and algorithm, Floyd-Warshall algorithm, right? And we will also provide practice problems in our practice set, so you can practice questions from there. Okay, so as today's class has been ended, so you guys may leave the meet.